case 2. Lambda equals 0. Well, if lambda is 0, then of course r is just 0. Therefore, x of x is just c1 times 1. So what are the solutions? One solution is just 1. The other one is x times 1, right? This is e to the power 0x, and this is x times e to the power 0x. So we have this. So this is x of t, x of x, sorry. And then when you plug the conditions again, x0 is 0, you get c1 is 0, xl is 0, you get c2 times l is 0, but l is positive number, therefore c2 is 0. So this again gives us only the 0 solution because both c1 and c2 are 0. So this gives us u equals 0 again. So no interesting solution in this case either. Therefore, we look at the third case where lambda is negative. So let me just do that. Ya da onu buraya yapmayayım hadi. Okay. Okay, so case 3, lambda is negative. In this case, so we had this equation, and r squared equals lambda, and it is negative. So let's say this is minus nu squared. Nu is positive. So r is just plus minus I times nu, purely imaginary. Therefore, x of x is just c1 times cosine nu x plus c2 sine nu x. And we have the initial conditions 0 and x of l is 0. So this gives what this first equation gives us. When I plug 0 here, we get c1 times 1 plus c2 times 0 equals 0. Therefore, we get c1 equals 0. And this means x of x can have only sine term in it, right? What about this one? X of L is 0, so C2 times sine mu times L is 0. Therefore, mu times L is just, well, either this is 0, but if C2 is also 0, then you get, again, 0 solution. So the only way to obtain a non-zero solution is that this sine mu L should be 0, and this is possible only if this is a multiple of pi, where k is an integer. Therefore, mu is just k pi over L, k being an integer. Therefore, lambda is just, it was just mu squared, right? minus mu squared, pardon. So it is just minus k pi over L squared. And in this case, what are the solutions for, okay, solution is just x of, let's say, k is just sine mu L, mu is just k pi over L, therefore it is just k pi x, right? Mu is just k pi over L divided by L, and k is an integer. So for x, we have this solution. What about t? T of t. T of t satisfies this condition. This divided by this is equal to lambda, and lambda is just this expression here, minus k pi over L squared. All right, so this is just this equation. The characteristic equation is just r squared minus lambda c. Therefore, r is, efendim, c squared. Evet. Yes. So it is just lambda times this. So minus k pi c over L squared. Therefore, r is just plus minus I times k pi c over L. I don't consider, lambda equals 0 or positive case, because in those cases we have no solution except the zero solution. Therefore, I can just concentrate on the case where lambda is equal to this gadget, right? Because the others gave me nothing but the zero solution. Yani tekrar aynı şeyleri yapmanın bir anlamı yok. All right, so we keep the boundary conditions, initial conditions in mind. Now from this we get what? All right, R is just, again, purely imaginary numbers. Therefore, the solutions are sine and cosine again. So we have the following solution. Tk of t is just what? Some number, let's say C1 times cosine R k pi c over LT. So the only difference is that we have this time an extra c term here, and then c2 sine k pi c t over L. Okay. So what is now for each k, for each integer, I have a solution for x and a solution for t. Therefore, we have a solution for u, and that is just x of kt x and tkt. So it is just sine is just multiplied with this. Therefore, we get something like this: c1 times okay, cosine k pi ct over L sine k pi x, ya da şöyle olsun, plus c2 sine k pi ct over L, and then the whole thing is multiplied with sine k pi x over L. All right, now for each k, I have one solution of the homogeneous equation, right? We have this homogeneous equation and homogeneous boundary conditions. Now, each one satisfies this equation and this equation. Since these are homogeneous, any linear combination of these is also a solution of the equation and the boundary conditions. Therefore, I may just take arbitrary linear combinations of these. And since these are actually, Fourier functions, right? I mean, periodic functions, I may just consider the Fourier series for this. So we get what? We get something like this. K, and here, of course, K is an integer. But you see, for negative K values, K sign, minus K goes out. This minus sign goes out, and cosine minus K will be observed. Therefore, for positive and negative values, you get the same functions basically, because we have, arbitrary coefficients in front of them anyway. So therefore, I don't have to consider negative values. It is enough to consider only non-negative ones, because for negative K values, I will not get something, extra. I will have the same functions. Therefore, I can just concentrate on non-negative K values. Therefore, I can write this from 0 to infinity, and then okay, now for each K, I will have a coefficient. So let me just write it this way: AK times cosine K pi CT over L plus BK times sine K pi CT over L, and then multiplied sine K pi X over L. Okay, so that's the general solution of the wave equation for finite string whose ends are attached to some fixed positions. So this is the general solution. Well, we were given an initial value problem and boundary value problem. Actually, initial boundary value problem. I have used the equation and the boundary conditions, but we didn't use the initial conditions. So we have to take care of the initial conditions. What were the initial conditions? Ux0 equals f of x, right? And u sub t x0, this is the initial velocity, which is g of x. This is the initial position of the wave. This is the initial position of initial velocity of the wave. When I plug t equals 0, let's see what we get. So I have here f of x, and when I plug t equals 0, right, ux0, so you plug t equals 0. When t is 0, cosine term will be 1, so you will have only ak. Sine 0, this will completely vanish. So I have only ak here. Therefore, we have ak times sine k pi x over L, k from 0 to infinity. Okay, of course, you know, a when you plug k equals 0, you get 0. Therefore, I can just start from 0 because there is no sign 0, right? It is the 0 function. So I can just write it this. And then we know what the coefficients are in this case. Efendim? So what is AK in this case? In this case, so AK is just 1 over 2 pi, right? 0 to L f of x sine k pi x over L dx. So we just compute these integrals and obtain AK, and then we obtained half of the solution. What about the other half? So AKs are obtained. What about BKs, right? Well, we have to use the other condition. Well, UT is this. I'm sorry, U is this function. So I need to take t derivative of this. Well, we will just take the t derivative, taking the t derivative of the inside. That's a theorem, of course, you know, when you can take derivative operator inside an infinite sum. That's not, you know, something immediate. It needs proof, but we will not deal with that. It is hayır, bunu çarpıyoruz tabii ki. Bu t bu x'ti ya. Değil mi? O türev toplamının içine nasıl girer? O 349'da göreceğiniz bir şey. Yes. Oh, didn't work. Yani işte teoremin koşullarına bakmanız lazım. Yani orada uniformly converge ediyorsa evet, yani burada onları sormayacağız. Evet. Mühendisler gibi düşünüyoruz burada. Okay, so we need to compute this derivative. What is this? So you just take t derivative of the series, and we just take derivative inside. So when you take derivative of cosine, you get minus ak times, so I have k times pi times c over L sine k pi c t over L plus bk, and then you take derivative k pi c over L cosine k pi c t over L, and the whole thing is multiplied with sine k pi x over L. Since this is a function of x, you know, it just stays as the same. And then we have the initial condition, right? When I plug 0 for x, we get gx. And here we have what? When I plug 0, well, for x, pardon, bunu yanlış yazdım, right? This is x, this is 0. Initial condition means t equals 0. So when I plug t equals 0, this becomes 0, so AKs are gone, and this becomes 1. Cosine 0 is just 1. Therefore, we have BK times K pi C over L times cosine, no, sine K pi X over L. All right, so then what is this gadget from the Fourier coefficients? Çok yaşa. So this coefficient is BK times K pi C over L is just, again, 2 over L, right? Efendim? Ha, bunu yanlış yazdık. This is 2 over L. Tabii seride de yanlış yaptık. Sıfır durumunu dışarı yazmamız lazım, değil mi? Şöyle, şurada bir düzeltme yapayım. Remember, for k equals 0, so I don't have to deal with b 0 because this is already 0. Here I should start from 1, and the k, no, k yerine 0 yazınca burası zaten 0, değil mi? Oradan aslında hiçbir şey gelmiyor zaten. Okay. Potentially, there is a 0 term here, but since k equals 0 just kills this guy, everything is gone. Therefore, I can just start from k equals 1. Okay, so I don't have to deal with. So it is 2 over L times integral 0 to L g of x, right, times sine k pi x over L dx. Therefore, bk is what? Bk is just, all right, so bk times this is equal to 2 over L times this. Therefore, this L's are gone, right? It's interesting. So in bk, there is no L. Well, there is L, of course, because L is here, but nevertheless, so it is just 2 over K pi C, and then 0 to L gx sine K pi x over L dx. C herhalde hani bu elektromanyetik dalga şeyinde ışık hızına denk geliyordur muhtemelen. O yüzden C kullanılıyor herhalde. Değil mi? Öyle olması lazım. Sen fizikte double major yapmıştın. Yok. Buraya gelmedik diyorsun. Tamam. Okey. Tamam. Ee, Şimdi kitapta hiç örnek yok notlarda. Neyse bir tane biz yapalım. Okay, so example. Solve the initial boundary value problem. U sub tt is equal to okay, U sub xx for x between 0 and 1, and then boundary conditions are 0 as usual, and the initial condition is okay. Bu da 1 olsun. Bir de 0 alalım. All right, so here c squared is 1, therefore c is 1. L is 1. Fx is just x times 1 minus x, and gx is just 0. Therefore, in the solution, we will have a case but no bk. Ya da istiyorsanız koyalım buraya bir şey. Bu da şeyden çok emin değilim de. Bu anlamlı bir şey mi, legal bir şey mi? Çünkü uç noktaları hareket etmediği için. Yani hız böyle olamaz. Neyse, e, deneyelim. Bakalım ne çıkacak. Initial position is this, right? So you see, initial position of the string is it is 0 at this point and 0 at this point. So it is x minus x squared. It's a parabola, right? Upside down parabola. So something like this. So this is the initial position of the string, and then you just let it, vibrate. Okay, now let's see what the solution is. All I have to do, just compute a case. A k is just 2 over L, 0 to L, f of x sine k pi x over L dx. Okay, so this is just 2 over 1, and then integral 0 to 1. F is just x times 1 minus x, and then sine k pi x dx. Well, this is several integration by parts, right? Nothing but integration by parts. Okay. Şöyle bir şunu açalım. Bu bir x çarpı sine k pi x over x dx minus 2, 0 to 1 x squared sine k pi x dx. All right, so let's see. Okay, so AK is 2 times. Now, for the first one, okay, so what is this integral? Let me just compute it here. So this is u, and this is dv. So this will be u times v minus 0 to 1 v times du. So that is equal to u is just x, v is so x, and then v is integral of this. So it is minus 1 over k pi cosine k pi x, right? 0 to 1 minus 0 to 1 v du. Du is just 1, so minus, and then I have this, so it's plus 1 over k pi cosine k pi x dx. Okay, integral of this is just sine, and when I plug 0 or 1, I get sine of an integer multiple of pi, which is just 0. So this integral will give me nothing. What about this one? When I plug 0, this is again 0. When I plug 1, I get cosine k times pi. So we get just what? This thing, this whole thing is equal to x yerine 1 yazdığımız zaman ne elde edeceğiz? Burası k pi olacak. Cosine k pi eksi 1 üzeri k. Bir tane daha var. Eksi 1 üzeri k plus 1 divided by k times pi. Right? Yani 1 koydum. X yerine eksi 1 üzeri, pardon, eksi 1 var. Cosinus k pi. Cosinus k pi is just minus 1 to the power k. Another minus, so minus 1 to the power k plus 1 divided by k times pi. So bk, the first term of bk is just no, ak, sorry. The first integral is just minus 1 to the power k plus 1 divided by k times pi minus this integral. Okay, minus ya da şöyle diyeyim, şöyleydi, 2 eksi 2 tane sıfırdan 1'e x kare sinüs k pi x. Ha. Şimdi buna integration by parts 2 kere yapacağız. Okay. U dv yapalım bir tane. UV yani x kare bu integralde neydi? Eksi 1 bölü k çarpı pi kosinüs k pi x 0 to 1 minus minus aslında plus 0 to 1. Bunun türevi 2x buradan da ne gelecek? Yine işte eksi 1, özür dilerim, kp cosine k pi x dx. Alright. Şurası ne verecek? X yerine 0 yazarsak 0 zaten. 1 yazarsam da 1 gelecek. Yani eksi 1 yazarsam kosinüs k pi, dolayısıyla eksi 1 üzeri n artı 1 x1 oldu. Bölü k pi. Tamam. Artı 2 tane. Şimdi şurada şu eksi işaretini ve kp'yi dışarı alalım. Burada ne kaldı? Sıfırdan 1'e x çarpı kosinüs k pi x dx. Aradaki nasıl artı oldu? Eksiydi. Bir dakika. Şimdi x kare bunun integrali buydu. Eksi 2 tane pardon, eksi bu 2 de niye geldi ki? Ha, x karenin türevi 2x. Bunun integralinden eksi var. Ama o eksi burada zaten. Dolayısıyla bu eksi. Değil mi? Burası eksi. Eksi şimdi artı oldu. Değil mi? Böyle yazabiliriz. Okey. Burada bir daha integration by parts yapacağız. U du dv pardon. Okey. Bu integral kısmı, yani UDV UV eksi VDU, bu da U nedir? X. Ve bunun integrali 1 bölü K pi sin K pi x 0 to 1. Bu 0 verecek çünkü K yerine, so when I plug x equals 1, I get sin K pi, which is 0. When I plug 0, I get 0. So this doesn't give us anything. I have only this 0 to 1. V du is just 1, and v is just 1 over k pi sine k pi x dx, and that is just integral of this is minus cosine, minus, it is plus 1 over k pi squared cosine k pi x 0 to 1. When I plug 0 and 1, so this is 1 over k times pi squared. When I plug 1, we get cosine k pi, so minus 1 to the power k, minus when I plug 0, I just get 1. Okay. So şurası şuna eşit oldu, değil mi? Bu kpy burada duruyor. Ee, e, Bu niye square oldu burada? Ha, bir integral daha aldık. Yok, bir dakika. Evet, tamam, bir integral daha aldık. Değil mi? Şurada square var. Yani şundan bağımsız olarak. U dv e, bu var. Sonra bir integral daha alınca tamam. O zaman şu integralin yerine şunu yazabiliriz. Değil mi? So I erase this and write instead 1 over k pi squared and then minus 1 to the power k minus 1. Okay, so this is, I guess this should be also k, right? Not n. Okay. Hangileri? Ama burada şunlar var. Şununla şu mu? Ha, anladım. Ee, ha, bu evet, şu ikisi aynı zaten. İyi. O zaman ne çıktı? Ee, Şuraya yazalım. Eksi 4 bölü k pi küp. Ondan sonra da evet, o da şu aslında. K even'sa 0 olacak. Odd'sa da e, burası eksi 1, eksi 1, eksi 2 olacak. Ya da şöyle yapabiliriz. Hatta okey. Ee, peki BK ne olacak? Yani olabilir. Belki anlamsız olabilir ama sorun değil. Evet. İyi, deneyelim bakalım ne çıkacak. So, neydi öbür condition? U sub t x 0. Buradan da gerçi buna gerek yok. Direkt b'yi yazıyorduk. N- aa, dur, neydi b? Bir sildik tabii. Dur, neydi bir? BK was 2 bölü K pi C değil mi? Sıfırdan L'ye kadar. Gx sin K pi x over. Okay, so L is 1, K pi C, 0 to 1. G was also 1, right? So sin K pi x dx. Buradan da ne çıkıyor? Eksi değil mi? 1 bölü K times pi çarpı kosinüs K pi x 0 to 1. So BK is just eksi 2 bölü K squared okay. K squared C squared no C pi squared C. C'nin square'i yok. Efendim? C1'de o yok. Kosinüs K pi minus 1. Okay. Bu da aynı şey değil mi? Evet. K oddsa yani şurası o zaman bu 2 olacak. Yani 4 tane tau squared pi squared. K oddsa eksi 1 eksi 1 eksi 2 4 ediyor. Yani 1 K odd 0 K even. Diğerine aynısını bulduk. Evet. Yani o zaman U xt şu olacak. Sadece oddlar için toplam var. K birden sonsuza kadar ama K odd 8 bölü K pi küpt neydi? Kosinüs K pi C1'di. T over L. L de 1. Minus ya da plus BK. O da 4 bölü K squared pi squared sinüs K pi T. Tüm bu nesne şeyle çarpılıyor. Sinüs K pi x. Okay. İyi. İyi. O zaman haftaya görüşürüz.